you and I'm here. Hello, everyone. This is Ceren. I'm pleased to introduce Ayşenur. She just finished her third year in Marmara University. So this summer, Ayşenur and I studied quantum computing. And this might be a little personal, but I want to say this. When I was a physics undergraduate, I really liked quantum physics and quantum information theory. And in the past years, I was always looking for an opportunity to study these topics again. So I would like to thank the RP for the opportunity, and many thanks to Ayşenur for being a great company along this nostalgic journey. So, okay, Ayşenur, take the stage.
Hello. First, I'd like to thank the organizers of the event because it's such a joy and opportunity to participate. I'd like to thank my mentor, Ceren Hocam, for all of her insight. I had such a wonderful time. She said that communicating your ideas in mathematics is really important. So considering that, you should give a presentation that you prefer to listen to. I mean, not the exact words, but meaning is preserved. So I'd like to try to do that as best as I could. We studied quantum computing in general. Today I'm going to talk about quantum computing and the Deutsch-Jozsa algorithm. To understand the Deutsch-Jozsa algorithm, first we need to have a tool set. So we're going to look at qubits, superposition, measurement, quantum gates, and quantum circuits. Then we are going to dive into the Deutsch-Jozsa algorithm. And then implement it on Qiskit, which is a Python library. Make calculations on computations on computers, you need two things. First, to encode the information, then to manipulate said information. In classical computers, we do this by using bits and logic gates. In quantum computers, we use quantum behaving objects to encode information, like photons or trapped ions. We call them all quantum bits, qubits for short. And to manipulate the information qubits port, we use quantum gates. So qubits, we show qubits with state notation. This is state 0, and this is state 1. We also can visualize them on the block sphere. Here you can see both of them. This is also our basis state we're going to use today to make calculations on. If we have more than one qubit and we want to examine them at once, we show them as the tensor product of the two as the qubits we have. If we have n qubits, we show it as n tensor power of the set qubits, as you can see. As you can see here for the 0 state. So superposition, any qubit exists in linear combination of states called superpositions. This here is a general qubit, and you can see it here on the block sphere. Since we have, oh, by the way, alpha and beta are complex numbers. Since block sphere has radius 1, we have a condition called normalization condition, which states that norm squared alpha plus norm squared beta must be equal to 1. So all qubits should preserve this condition at all times. Also, alpha and beta are called probability amplitudes. What I mean by that is qubits carries probabilistic information about what states they want to be closer to. They prefer more to collapse to. So when we extract this information, we measure the qubit. This here is a meter, a measuring device. After measuring the qubit, what we have is state 0 with probability norm squared alpha, and with state 1 with probability norm squared beta. So quantum gates, we use quantum gates, as I said, to manipulate the information. Since qubits must preserve the normalization condition at all times, quantum gates must be unitary matrices, and that means that they are reversible. There are as many quantum gates as there are unitary matrices, but we're going to look at just a couple of them today, the kind of important ones. The Hadamard gate and Pauli X, Y, and Z gate. So the Hadamard gate, it creates superpositions, takes the states and map them to other states, takes state 0 and maps it to state plus, and takes state 1 and maps it to state 0, minus 5. This is its matrix representation. And we can show it like that in a circuit. So these are the Pauli gates. Pauli X gate here flips the state. And you can observe Y and Z here. This is a basic quantum circuit. We can build quantum circuits combining different gates. So this one, what this does is it takes state 0 and superpose it using Hadamard gate. Then X gate flips the states, as you can see here. And then when we measure, what we have is state 0 with 50% probability and state 1 with 50% probability. So far I provide you with enough information. Now let's think about this problem. What we have here is an n-length binary function. We know that it's either constant or balanced. By the way, but balanced, when I say balanced, I mean that it maps half of the inputs to 0 and the other half to 1. Let's examine this for n equals 1. Now we have 2 inputs and 2 outputs. That means we have 4 possible configurations for function's behavior. When we look at that, if we want to determine the function's behavior using classical computers, what we do is we evaluate the function. There is not much that we can do because we don't know the exact specifics of what the function do. So let's say we start evaluating from 0. What we would get is here 0. If the f0, if f0 equals f0, that doesn't give that's not really meaningful because the problem is still here. I still don't know the function is constant or balanced. It's the same case for if output is 1. So to determine the function's behavior, what I must do is I need to evaluate f1, 2. So that means 2 evaluation. And that also means executing the program 2 times, which gives us the complexity class O2. And for any n, this equals n minus 1 power of 2 plus 1, because we need to evaluate the function sorry. One more than half of the input. Number of half of the input. But in quantum computing, we don't even need to evaluate the function, and executing the program one time is enough. So that gives us the complexity plus O1, which is the same as for any n, which is as simple as it could get. So how do we do that? We do that by using the Deutsch-Jozsa algorithm. This is the circuit for n equals 1. N is the number of 0 qubits here. We know the Hadamard gates, and this is a meter to measure. UF here, what UF does is, U is the first letter for unitary, as in unitary matrices. So UF means unitary matrices that, a unitary matrix that unitary matrix relating to function F. What UF does is, it maps X and Y, which are outputs of Hadamard, respectively to X tensor product, Y mod 2 sum Fx. The use of that is, we built the UF like that because we want it to behave like the function, so we can have ideas about the function without evaluating it. Just passing some inputs through UF gives us ideas about Fx, the function. The size here are pointing out different stages of the algorithm. When we reach the stage 3, what we have is ket 0, ket minus, and what we might have is ket 0, ket minus, or ket 1, ket minus. If F is constant, if we have ket 0, ket minus, then we know that F is constant. And if we have ket 1, ket minus, then if we know that F is balanced. And we can generalize that for any n. These are n many zero state qubits as before. So again, it's the same. If we have state 1, then we can say F is constant, and if we have state 0, sorry, then we can say F is constant, and if we have state 1, then we can say F is balanced. Now time to implement it on Qiskit. Here, what we do is we add the libraries that we need. IBM-Q here is, we can use IBM's own quantum computers and make calculations on them by requesting it. So this package does that, and AR gives us the ability to make simulation. We will evaluate the execute the algorithm for n equals 1. So we will have five qubits as input. Here, what we do is we build the UF. And then we build the circuits. In the first part, we are building a kind of a we are building kind of a skeleton for the circuit to add things on. And then we add X gate and Hadamard gate to the first qubit. The use of X gate here is here at the circuit. We have one as input, but in Qiskit the default qubit state is 0, so we want to flip it. To do that, we add an X gate. After that, we add Hadamard gates and add our oracle. Then the Hadamard gates again, then we measure. When we visualize it, we have this picture and we choose our function as to be constant for this version. And after evaluating the function and executing the algorithm in simulation, what we have is, because the function is constant, what we have is 100% with 100, state 0 with 100% probability. If we the version function is balanced, what we have after simulation is the 100% once state 1 with 100% probability. So that's the end of my talk. If for further reading, Qiskit.org is very intuitive, good resource to start out. For more academic approach, you can check out Nelson's book.